Today we will talk about estimating population proportions using representative samples. And I will begin with an example where I consider the following statement. 2% of Americans have been diagnosed with OCD. The quantity of interest here is a population proportion. We might not know the population size, but in this example, we do know that 2% of Americans have been diagnosed with OCD. And this is an example of what is called a dichotomous population. An individual in a dichotomous population either has a trait or does not have that trait. So either an individual has been diagnosed with OCD or they have not. Another example could be an individual has blue eyes or they do not have blue eyes. We're now going to estimate population proportions using what is called a sample proportion. So our definition is that the sample proportion is an estimate of the population proportion given by y over n. And we refer to that sample proportion as p hat. Y here is the number of observations that have a particular trait, and n is the total sample size. So if we survey 100 Americans and 2 of them say that they have been diagnosed with OCD, our sample population proportion would be 2 out of 100, or 2% of Americans have been diagnosed with OCD. Let me move on to another example. So here, recent research has shown that soda fountains can contain bacteria that cause illness. Suppose researchers sample 30 soda dispensers and find that 5 are contaminated. What proportion of machines in general are contaminated? Well, we don't have a count of all of the soda dispensers that exist, but what we do have is a representative sample of 30 soda dispensers. And we know that p hat is 5 out of 30, which is approximately 16.67% of soda machines are contaminated with bacteria. This will make you think twice about using that freestyle machine in the caf. Well, what if our sample had been smaller? What if the sample only contained 2 soda dispensers and 0 were infected? Then p hat in this instance would be 0 out of 2, which is 0, and we would estimate that 0% of soda dispensers are infected. Do you think that this estimate will be accurate? Well, no, we do suppose that maybe some of the soda fountains will have that bacteria that can cause illness. So let's talk about some of the drawbacks of using p hat to estimate population proportion. P hat assumes that there's actually a normal distribution, but for a dichotomous population, the distribution is in fact binomial. Here, each individual either has a trait or does not have the trait, and we're going to count up all the individuals that do have that trait. And that corresponds to our definition of the binomial distribution. An observation in this case is either positive or negative, or true or false. And the confidence intervals for p hat turn out not to be very reliable. So what we would like to do is make an adjustment to our population proportion so that we don't have examples like the one we saw above where we ended up estimating that 0% of the dispensers were infected. So we will consider an adjustment, and this adjustment was made in 1927 by Edwin Wilson, and he discovered a correction that gives a normal-based confidence interval that better fits the underlying binomial distribution. And so the Wilson adjusted sample proportion is an estimate of the population proportion that's given by p tilde. And p tilde is y in the numerator and n in the denominator. But here in the numerator, we're going to add 1/2 z sub alpha over 2 squared. And in the denominator, we're going to add z sub alpha over 2 squared. Here, y is the number of observations, n is the sample size, and z sub alpha over 2 is the top alpha over 2 percentile of the normal distribution. So before we would see something like t sub alpha over 2, and that was the top alpha over 2 percentile of the t distribution. But now z sub alpha over 2 is going to be the top alpha over 2 percentile of the normal distribution. Okay, so what is p tilde if alpha is 0.05, which is a common alpha that we often use? Well, p tilde in this instance is y plus 1/2 z 0.025 squared over n plus z 0.025 squared. Okay, so that's y plus. Now, what is the top 2.5 percentile of the normal distribution? Well, the number is a number you should recognize. It's 1.96. So if we were to draw a normal distribution, you'll have to forgive my normal distribution. We'll try one more time. We saw before that at 1.96 and say negative 1.96, we can define the middle 95% of the normal distribution, which means above it is 0.025 and below it is 0.025. So in fact, let me put, instead of 95%, 0.95 for the area between negative 1.96 and 1.96. Okay, so that's the top 2.5 percentile of the normal distribution. And then in the denominator, we have n plus 1.96 squared. That gives us y plus 1.92 over n plus 3.84, which is 1.96 squared. Now, what is often done is that this is approximated as y plus 2, since 1.92 is close to 2, over n plus 4. And so when alpha is 0.05, we often use y plus 2 over n plus 4. The significance of this is we can think about the fact that we're adding an additional, or we're adding 4 trials to our sample. And here 2 are successes or positive, and 2 are failures. So let's use the Wilson adjusted sample proportion to estimate the number of soda dispensers that are contaminated. Okay, so here we have p tilde is 5 plus 2, because we're adding 2 success trials, over 30, which is our n, plus 4, which is a total of 4 additional trials. So we end up getting 7 out of 34, which is approximately 0.2059. or 20.59% of soda dispensers are infected. So a little bit more than the 16.67% that we had gotten earlier. So how does P tilde compare to P hat? Well, let's go back to our example where we had 2 machines that we sampled. Well, if we sampled that 0 out of 2 machines were infected, initially P hat would have been 0 over 2, or 0% are infected, but P tilde is going to be 0 plus 2 out of 2 plus 4, and so that is 2 out of 6, which is 1/3. Okay, and so that says about 33% of our machines are contaminated, which is probably closer to reality than 0. Now, if we have 1 out of 2 are infected, then P hat is 1/2. P tilde, on the other hand, is 1 infected plus 2 over 2 total plus 4. That ends up being 3/6 or 1/2. And you can see that when P hat is 1/2, that P tilde is also 1/2. It's unchanged. Now, what if 2 out of 2 of the dispensers are infected? Well, then P hat is 2 out of 2, which is 1. So that's saying 100% are infected. But P tilde says 2 are infected, plus we add 2 additional out of a total of 2 plus 4 additional. So that gives us 4/6 or 2/3, which says that 66.66% are infected, which is probably closer to reality than 100% are infected. So we'll note that P tilde is less likely to estimate that P is 0 or 1. So P tilde in general is less extreme. It is going to push our proportions a little bit closer to 50%. We saw that with the soda dispensers that were 16.67% infected, and now P tilde is pushing it a little closer to 50% with 20.59% infected. So what I'd like to do is create confidence intervals around these proportions. And so in order to do that, we have to have a notion of standard error. So to compute the standard error, we're going to recall that the variance of a binomial random variable y is given by the variance of y, which is np times 1 minus p. Now, our P hat, which is going to estimate population proportion, is given by y over n. So we think about y as being a random variable that's counting the number of individuals that have that trait in our population. So what is the variance of y over n? Well, you may recall that when you have a constant inside the variance, that you can bring it outside, but you also have to square it. So we get 1 over n squared times the variance of y. We know the variance of y, it's n times p times 1 minus p. And so we can divide that by n squared. And so the variance of y over n ends up being p times 1 minus p over n. The standard error of P hat then, of course, is the square root of the variance of P hat. So standard error is going to be the square root of the variance of P hat, or y over n. And so that's going to be the square root of p times 1 minus p over n. So here we've defined our standard error okay, to be the standard deviation of our population proportion, and it's given by this formula of square root of p times 1 minus p over n. Now, I did this for p hat, but I also could have done this for p tilde, and I'll show you that the result is similar. So the standard error of p tilde turns out to be the square root, and the numerator is similar, p tilde times 1 minus p tilde. Okay, but instead we're going to divide by not n, but n plus z sub alpha over 2 squared, which was our denominator for p tilde. For a 95% significance level, we're going to simplify this to the square root of p tilde times 1 minus p tilde over n plus 4, because z sub alpha over 2 squared is approximately 4. Now that we have our standard error, we can construct our confidence intervals. So let's remember what a confidence interval looked like before. Before, we were estimating confidence interval for the mean. So we had y bar plus or minus, and then we would use t sub alpha over 2 with the degrees of freedom times our standard error of y bar. And for a single sample, that was just that was sigma over square root of n. But for a population proportion, we're going to end up using the normal distribution instead of the t-distribution. This is because for large n, the central limit theorem is going to tell us that the sampling distribution for p tilde, which is binomial, but for large n is going to be approximately normal. So instead of using the t-distribution, we're actually going to be using the normal distribution. You might recall the reason we switched the t-distribution was because we were having to estimate standard error using sample standard deviation because we didn't know the true standard deviation. Here, we don't have to do that because there isn't a standard deviation involved. Instead, we're using p tilde to help us estimate the standard error. So I'm going to define the confidence interval for p tilde. Okay, so it's going to be p tilde plus or minus. Instead of a t value, we're going to use z sub alpha over 2. And then that's going to be times the square root of p tilde times 1 minus p tilde. Let me make sure that those tildes look like good tildes. Divided by n plus z sub alpha over 2 squared. And for 95% confidence, we're going to write this as p tilde plus or minus 1.96 times the square root of p tilde times 1 minus p tilde over n plus 4. So a lot of the times we're going to be computing just 95% confidence intervals, so it's nice to be able to just say that z sub alpha over 2 squared is approximately 4. And so you can see that our confidence interval has that same format that it did for the mean, where we take the quantity of interest, which before was the mean and now is p tilde. We add to it a number that's close to 2, kind of defining the 95%, and then times the standard error, which in this case, the standard error is given by that formula. So there's some symmetry to how we construct these confidence intervals. So I now want to conclude with an example. So my example is, suppose that 5 out of 30 soda dispensers are contaminated. Find a 95% confidence interval for the population proportion. So we saw before that p tilde was 5 plus 2 over 30 plus 4, which is 7 out of 34, or approximately 20.59%. Our standard error for p tilde is going to be the square root of 0.2059 times 1 minus 0.2059 over 30 plus 4, which is approximately 0.0706. So in this case, our confidence interval looks like p tilde plus or minus 1.96 standard errors, which ends up being 0.2059 plus or minus 1.96 times 0.0706. This interval works out to 0.0675 to 0.3443. So we can say we are 95% confident that the true proportion of infected or contaminated dispensers is 6.75 to 34.43%. And what we mean is that we took repeated samples of 30 soda dispensers. 95% of the intervals that we construct would contain that true proportion of contaminated soda dispensers. I'm going to give you one more example. This example is our OCD example. It says OCD is often underdiagnosed, and suppose that 6 out of 20 randomly selected individuals are diagnosed with OCD. Estimate the proportion of the population that has OCD and include a 95% confidence interval. I'm going to give you a moment to work through this problem so that you can find the population proportion, the standard error, and then the confidence interval. So you can pause this video, work on the problem, and then I will go ahead and go over the solution. Assuming that you've now worked the problem, we're going to estimate that p tilde is 6 plus 2 out of 20 plus 4. That's our adjusted population proportion, which gives us 8 out of 24, or 1/3. Okay. So our standard error of p tilde ends up being the square root. I'm going to go ahead and just use 1/3 here exactly because I can. So it's 1/3 times 1 minus 1/3 over 20 plus 4. So that's p tilde times 1 minus p tilde over 20 plus 4. This ends up being approximately 0.0962. And so our confidence interval is p tilde plus or minus 1.96 times the standard error, which in this case is 0.3333 plus or minus 1.96 times 0.0962. So this gives us a confidence interval of 0.1447 to 0.5219. So based on this sample, we would say we are 95% confident that 14.47% to 52.19% of people have been diagnosed with OCD. And there you have it. I do want to make one final note. The one final note I would like to make is that if you look at the standard error of p tilde, which is the square root of p tilde times 1 minus p tilde over, say, n plus 4, you can say that this is less than or equal to the square root of 1/2 as an estimate for p tilde times 1/2 over n plus 4. And that is because this function p times 1 minus p is maximized at p equals 1/2. You can do a little calculus if you like to see that that's true. So if we work this out, we'll get 1/2 times the square root of 1 over n plus 4. So sometimes when people don't feel good about their estimates of p tilde, they will say that the standard error is 1/2 times the square root of 1 over n plus 4 because that's the biggest that the standard error could possibly be. And I found that when looking at political polls that this is exactly what they end up using for standard error. So instead of plugging in for p tilde, they instead estimate it to be 1/2 so that the standard error is as big as it could possibly be.